Yeah, I'd like to thank the organizers for the invitation. I'd like to talk about the evolution of the AMOC during the last deglaciation, about some forcing mechanism and instability. This is work mostly by student Wei Liu, who is now at Scripps PhD thesis, and also Jiang Zhu is a student there, in collaboration with NCAR, Brady. So we have been doing this with Betty, our listener at NCAR. We have been doing this transient simulation the last 21,000 years with NCAR CGCM3. You can see that we use realistic CO2 forcing, orbital forcing, melting water, etc. Greenland temperature, more or less reasonable. We also have other papers showing the climate, global climate, and inter-hemisphere gradient seems to be very reasonable. Now, in this talk, we're going to focus on the Atlantic Meridional overturning circulation, compared with Jerry McMahon Practitioner theorem, AMOC. So in this case, you can see clearly H1 and younger dryer and recurring, more or less follow the observation. And also, interesting, I should point it out here that at LGM, we do simulate this delta C13 shallowing signal and at LGM, which is a very robust signal for LGM thermohaline circulation. And we don't have delta C13, but we have salinity. You can see more or less this feature. Now, there are two questions I'm going to address here. First of all, there is, of course, this abrupt change. So we'll say that what is the mechanism of this? I'll come back to this in a minute. But the other question is that in spite of all the change in CO2, everything, the strength of AMOC is actually comparable between LGM and Holocene. So this actually is kind of interesting in the simulation. And also, because the observation, we don't really have the proxy for the strength. So it's really hard to tell this in the observation. So, but it's interesting to think of this in the model context. Just looking at this in more detail, this is the AMOC, the black line alone in the trace simulation. And then to understand this simulation, we performed a few single forcing simulation. That is, we use the forcing individually. The red one is the one use just CO2, so AMOC increased. This global temperature increased. The green one is the one you have the ice sheet retreat, so AMOC decreased and temperature increased. And the blue one is one just putting melting water, so you can see all the millennial variability. The orbital one is weak. Now, the first thing is that you can see that clearly the millennial variability is melting water, that's obvious. What is interesting, however, is that if you use CO2 alone, increase CO2, the AMOC should be intensified significantly. And the other one, this is decreased. So finally, they are about the same, comparable. Now, just this alone is interesting because we always have this impression that for the increased CO2, AMOC should decrease, but this is increasing. So how does that work? Now, I won't go to the details of this. We have a paper on this. Basically, what happened is that for the future CO2 scenario, most of this, we're doing a very rapid CO2 increase. In the initial stage, decadal to centennial timescale, the heat flux dominant. Reduced heat flux, reduced convection, therefore AMOC is indeed reduced. That's also true in this model. You can see the pre-industrial here. Okay. However, the difference for this from this is that, first of all, the time scale is much longer, centennial to millennial time scale. At this time scale, two other mechanisms start to function. One is that you have the sea ice retreat. So you have less freshwater import from Arctic melting water. Therefore, therefore, the AMOC will be increased. The other one is that the Southern Ocean, the sea ice retreat, you have less brine injection that reduces Antarctic bottom water that helps AMOC to intensify. And this occurs at about 100 to 300 years. This is at a further longer time scale. So these two processes, longer time scale, especially, they are all related to sea ice, especially significant during the glacial period. In the modern day, it's less significant. So that explains why in this case, you actually AMOC increased instead of decreased like present day. Now, on top of that, because you have the reduced retreat of ice sheet, and then what happened is that the surface wind over North Atlantic is intensified. Therefore, you expand the sea ice, so you cut off the heat loss. So that results a lowering of the AMOC. So finally, you ended up here. And I'll switch to another topic about the instability. Now, I showed this figure. You see the Greenland temperature AMOC seems to be reasonable, but it's actually, in some sense, it's cheated because the abruptness, the red line, is really coming from the melting water. Artificially, you make it abrupt. Otherwise, if we use this blue line, melting water gradually, in the model, it just gradually come up. So you don't have this abrupt boiling out of warming. Now, that's because in this model, basically, there's no multiple equilibrium. It's monostable. Now, that wouldn't be interesting given, because otherwise, well, it is interesting because this is not a special just in CGCM3. In most of coupled general circulation model, they tend to show similar behavior. That is, when you host it, it dies. When the host goes away, it comes back in most of the general circulation models. So, so that is interesting. Says that the abrupt change cannot in the model cannot be caused by the AMOC instability itself. Now there are other models, especially for intermediate model, which can produce all those very nonlinear hysteresis. So these models you can actually indeed produce abrupt change if you just have a smooth change of melting water. So the model can produce different behavior. Especially curious is that why coupled general circulation model, they don't produce abrupt change. Now, ultimately, we have to think about in terms of observation. Now, one way, think about paleo observation. In this case, ideally, you should have very accurate chronology of the melting water relative to AMOC. And, but I wouldn't, because it's very hard to construct very accurate chronology of melting water. So, I think this is still ambiguous. It's not obvious, okay, if this were either way, okay. Now, the other way is that we say, well, what about if you use the present day modern data, right? Now, for present day, you have a problem because you don't have this collapse events. So what you can do is that if you work, it will have to have a stability indicator, diagnostic indicator. You cannot do a simulation. Now, fortunately, a while ago, some Ramstaff developed an interesting idea using box models saying that the freshwater transport along the South Atlantic could be used as an indicator. And if it's export, then it's unstable. If it's import, then it's stable. And now it hasn't been completely shown in complex model, okay? But it has some legitimate point can be applied. Now let's assume this is okay. Okay, if you assume that this is okay, you diagnose the present day observation. Use different reanalysis data at different years, or use direct observation. They are indeed negative, means they are exporting. So in the observation, they tend to show they are bistable in the real world. However, in CGCM, I'm just showing one example. Look at the green lines. Most of them, they are positive. So they are actually, it's importing instead of exporting. So this does show that in coupled general circulation model, they tend to be stable instead of like the observation. So the next question is that, is this indicator really accurate? And I will show you in a minute, more or less okay, but you have to add a modification. The other question is that if the model are biased towards monostable because wrong direction of the freshwater transport, why is it? Why the freshwater transport is wrong? What is causing that bias? Well, I would say that one, at least, part of the reason will be the so-called tropical bias. Now, this experiment, CGCM3, shows that if you use sourceward transport as indicator, now this is slightly negative. You would expect the model is bistable, but it's not. You do a hosting, it comes back, it's stable. So what you need to do is actually consider the total convergence divergence, not only in the south, but also include the freshwater import from the north. Now, in that case, this will be the difference between the two. It will be the black line. So it is indeed positive convergence. So it is stable in this model. So it's stable. Now, for a reason I'll talk about in a minute, you do another scenario, you do a flux correction to the model. So the model is more or less like the present-day observation in the surface. In this case, the model, the convergence become divergence because of the change of the freshwater transport. In this case, now the indicator shows it should be unstable, and you do a hosting experiment. Indeed, it is unstable. Okay, so the indicator, you need to do a total convergence instead of just South Atlantic. But this point is interesting. Why, when you correct to flux adjustment, it's more or less like a present-day observation, then your model becomes unstable. Then this will be more consistent with the diagnosed observation we talk about. Now, looking at this, what happened is that we know the thermohaline goes northward here, goes southward here. Why it has a freshwater export is because the surface, the upper ocean are saline, like this black line. This is the observer Levitas salinity. So you import saline water, exporting fresher water. Northland deep water is salty compared to entire bottom water, but it's much fresher than the surface water. So you import salty water there. Or another way, you're exporting fresh water, either way. Okay? So in this case, in the observed state, you can indeed form this exporting fresh water in the observation. Now, in the model, why it's all wrong? Look at, these are all the models. Okay, those models, they're too fresh in the surface. If it's too fresh surface, you don't have enough salt import here, so then the net freshwater transport is reduced. Instead of exporting, it becomes importing. So all the CGCM becomes implied stable. Now, there are another type of model, dashed line here, it's kind of for you to see here, some model here. Now, those, you do have the salinity similar to the observation. Those are the models that with the flux correction. Of course, first flux correction, the surface is right, then you can make this right. Now, why the melting transport is wrong? Now, this surface gives us some clue here. Surface is too fresh if you don't correct it. Now, there's one reason, at least this is consistent across all the current CGCM without flux correction. That's tropical bias. It shows up here. So is this you see the precipitation? It's basically a double ITCZ problem, right? Compare with observation, too much fresh water in the south. ITCZ move back and forth, too warm, therefore too fresh. Okay, so if you do flux correction like this model, then the flux more or less correct, then surface salinity is about right, then your overturning freshwater transport is about correct. So, so that suggests that the tropical bias is potentially causing this model bias. So finally, we just come back to this. I showed this before with observation. We used the 0 as the line judging stability. That is, we only use South Atlantic transport. Now, if you consider North Atlantic, you should use this as judging line. So they shouldn't be as unstable as it was implied before. But probably you judge yourself. It's still probably weakly bistable, especially direct observation. I'm almost done here. And you can check this with different models. If you use no flux correction, the convergence, they are all CGCM. They are all convergent, so they are stable. Once you use flux correction, they become unstable. So this is the conclusion. For the AMOC, the evolution, the interesting feature is that the evolution is caused by the increase by CO2 rise. However, it is also canceled by the reduction of the ice sheet retreat induced AMOC change. And the implication is that the time scale is different, state dependent, and so the AMOC change during the deglaciation cannot be directly used for future climate change. For AMOC stability, it shows that the present observation probably is in weakly bistable, but the current state of GCMs, because particularly tropical bias, they tend to be biased not only in tropical precipitation, but also directly affecting the stability of the AMOC. So the model might be too stable. Yeah. Thank you.
If there are no questions, is there any question? Otherwise, we will proceed. Oh, there's one quick question, Garrett.
I think also the Atlantic is too fresh due to the fact that the warm water route from the Indian Ocean to the Atlantic is underestimated the most. It's also not only the hydrological cycle, but also the warm water route is.
Yeah, that's why I said it's at least. The thing puzzling is the following: why all the models show this? You know, individual model, you say Atlantic, Indian Ocean, maybe. What we do know that the tropical bias is common across all the models. So, you know, that becomes systematic issue. Once you do flux contraction, they change. So I'm sure there are other reasons. If you change intermediate water, other things, you change transport, many things. So I think there are other things need to be studied. But I feel the tropical bias, at least, is one common bias. You know. Thank you.